Welcome. You have nothing to do right now, nowhere to be, nothing to figure out. Simply let your body settle, let your breathing slow, and allow the quiet to hold you. Tonight, we are going to drift gently through the universe together, moving among the stars, those ancient, glowing companions that have watched over sleeping worlds for billions of years. There is nothing here but softness and wonder. Let it carry you. Our own Sun is a G-type main sequence star, one of the most common kinds of star in the universe. It sits comfortably in the middle of the stellar spectrum, not too hot, not too cool, burning with a steady golden warmth. Scientists classify stars by their temperature and color, and the Sun belongs to a broad, gentle family of yellow-white stars that have quietly lit the cosmos for billions upon billions of years. About 70% of all stars in the Milky Way are red dwarf stars. That means for every star like our Sun, there are many more that are smaller, cooler, and far dimmer. Red dwarfs glow with a deep, ruddy warmth, like embers rather than flames. They are so faint that not a single one is visible to the naked eye from Earth, and yet they quietly fill our galaxy in extraordinary numbers, patient and unhurried. Red dwarfs burn so slowly that they can live for trillions of years. Our Sun will shine for about 10 billion years in total. A red dwarf, by contrast, may burn steadily for 100 trillion years or more, a span of time so vast it is almost impossible to hold in the mind. They are the most patient things in the universe, sipping their fuel so gently that the cosmos itself may grow cold before they finally dim. Proxima Centauri, the nearest star to our Sun, is one of these quiet red dwarfs. It lies about 4.2 light-years away, our closest stellar neighbor, and yet it shines so faintly that you could never spot it without a telescope. It is a small, cool world of slow fire, circling through the dark at the edge of our stellar neighborhood, a gentle presence just beyond our reach, burning on its own unhurried timescale. Orange dwarf stars, like Alpha Centauri b, sit just a step above red dwarfs in size and warmth. Alpha Centauri b is part of the nearest star system to our own, traveling through space alongside its brighter companion. Orange dwarfs glow with a rich amber light, slightly warmer than a red dwarf, but still far cooler than our Sun. They are long-lived, stable, and steady, calm beacons in the slow river of cosmic time. Blue main sequence stars burn far hotter and faster than yellow stars like our Sun. Where the Sun glows a gentle gold, blue stars blaze at tens of thousands of degrees, pouring out enormous amounts of energy in ultraviolet and visible light. They are brilliant and extravagant, living fast and burning bright, but their intensity comes at a cost. They exhaust their fuel in only a few million years, a brief flicker compared to the long, quiet lives of smaller stars. Our Sun will eventually exhaust its hydrogen fuel in about 5 billion years. That is a span of time almost impossible to imagine, longer than the Earth has existed, longer than life has been evolving. For now, the Sun burns steadily and reliably, as it has for 4.5 billion years already. Its future is written in the physics of stars, and it will unfold slowly, peacefully, across an ocean of time that dwarfs anything human minds have ever known. When a star like the Sun finally runs out of hydrogen fuel in its core, it begins to expand into a red giant. The core contracts and heats up, while the outer layers swell outward in response, growing cooler and redder as they spread. It is not a violent event, but a slow, inevitable transformation, a star gently changing its form after billions of years of faithful burning, like a candle flame softening and widening toward the end of a long, quiet night. Betelgeuse is a red supergiant so enormous that if it were placed at the center of our solar system, it would swallow Mercury, Venus, Earth, Mars, and extend all the way out to Jupiter's orbit. It glows with a deep, ruddy warmth in the shoulder of the constellation Orion, one of the most recognizable stars in our night sky. Despite its immensity, It sits there quietly among the other stars, a vast, slow world of ancient fire drifting through its final chapter. Let yourself settle a little more deeply now. Feel the weight of your body resting, fully supported, held gently in place. There is nothing to figure out, nothing to remember, nothing to do. Let your breath slow on its own, easy and natural. Each exhale carries a little more tension away. Each inhale brings something quieter, something softer. You are drifting now, gently, like a leaf on still water, carried along without effort. Rigel is a blue supergiant, shining with the luminosity of 120,000 suns. It sits in the lower right corner of Orion, a point of cool blue-white light that has guided travelers and dreamers for thousands of years. Despite its staggering brightness, it appears to us as nothing more than a quiet, steady gem set in the dark. All that blazing energy crosses hundreds of light years and arrives at our eyes as a soft, still glow. Hypergiants are the most massive stars currently known to exist. They sit at the very top of the stellar family, rare and extraordinary, burning with an intensity that strains the limits of what physics allows. Most stars will never come close to this scale. Hypergiants are so luminous that their own radiation pushes against their outer layers, making them restless and unstable. They are the grandest things the universe has managed to build from gas and gravity. Auyai Scuti was once considered the largest known star by volume. Located about 5,000 light-years away in the constellation Scutum, it is a red supergiant of almost incomprehensible size. If placed at the center of our solar system, it would extend well beyond the orbit of Jupiter. Measurements of stellar sizes carry some uncertainty, and other stars have since challenged its record. But Auyai Scuti remains one of the most vivid examples of just how vast a single star can become. R136. A 1 is one of the most massive stars ever measured, exceeding 150 times the mass of our Sun. It lives at the heart of a dense star cluster in the Large Magellanic Cloud, blazing with an almost incomprehensible luminosity. Scientists believe it may have formed through the merger of several large stars early in its life. It is so extreme that its very existence pushes the boundaries of what stellar physics says should be possible. After a red giant phase, a sun-like star sheds its outer layers as a planetary nebula. The name is a gentle misnomer. These have nothing to do with planets. As the star's outer envelope drifts away, it forms a slowly expanding shell of glowing gas, illuminated from within by the hot core left behind. Each planetary nebula is unique, shaped by winds and rotation into rings, butterflies, and softly glowing spheres, brief flowers of light in the long darkness of space. A planetary nebula glows for tens of thousands of years before slowly fading. On human timescales that seems enormous, but in the life of the universe, it is a brief, luminous breath, a star quietly releasing what it no longer needs. The expanding shell of gas grows thinner and cooler over time, its colors softening, its light dimming, until at last it disperses invisibly into the surrounding space. The material does not disappear, it simply becomes part of the great quiet reservoir between the stars. The remaining core of a sun-like star becomes a white dwarf. After the outer layers have drifted away into a planetary nebula, what remains is a dense, compact ember, the heart of a star, stripped bare and left to cool in the silence of space. It no longer fuses anything. It simply glows with the stored heat of billions of years, radiating gently and steadily into the dark. A white dwarf is a star in its final quiet chapter, still warm, still luminous, but no longer burning. White dwarfs are roughly the size of Earth, yet they contain about half the mass of the Sun. That contrast is one of the quieter wonders of stellar physics, all that solar material compressed into a sphere, no larger than our own small world. The gravity at a white dwarf's surface is enormous, many hundreds of thousands of times stronger than what we feel here on Earth. and yet from a distance, it simply appears as a small, faint point of light, patient and still. A white dwarf is so dense that a single teaspoon of its material would weigh several tons here on Earth. The atoms inside are packed together far more tightly than anything we encounter in ordinary life, held in place not by nuclear fusion, but by a quantum pressure between electrons called electron degeneracy pressure. It is a kind of stillness written into the laws of physics themselves, matter compressed to its quietest, most enduring form, resting in the dark between the stars. White dwarfs cool slowly over billions of years, quietly radiating their stored heat into space. There is no fusion happening inside, no new energy being made, only the long, gentle release of warmth gathered over a stellar lifetime. The process is extraordinarily unhurried. A white dwarf may take longer than the current age of the universe to cool even partway. It simply glows and waits, and slowly, peacefully dims across timescales too vast to fully imagine. Let your body settle a little deeper now. Feel the weight of your limbs release into whatever is holding you. There is nowhere to go, nothing to remember, nothing to solve. Let each breath come a little slower, a little softer. You are safe and still, and the night is quiet all around you. Let your thoughts drift like wisps of cloud, unhurried and unimportant, dissolving gently as you rest. The hottest known white dwarfs burn at surface temperatures exceeding 200,000 Kelvin. That is many times hotter than the surface of our own sun, which glows at roughly 5,800 Kelvin. These freshly formed white dwarfs have only recently shed their outer layers and still blaze with intense ultraviolet light. Over millions and billions of years, they will cool and soften, but in their youth, they shine with a fierce, quiet brilliance all their own. Some white dwarfs develop surfaces composed almost entirely of pure carbon crystal. As the interior cools past a certain temperature, the carbon and oxygen atoms inside begin to arrange themselves into an ordered lattice, a vast, three-dimensional crystal structure stretching across the entire interior of the star. Scientists believe this crystallization begins deep within and slowly spreads outward over billions of years, transforming the white dwarf from the inside quietly and completely. A crystallized white dwarf is sometimes called a cosmic diamond in space. The comparison is not merely poetic. The internal structure of a crystallized white dwarf is genuinely similar to the atomic arrangement found in a diamond, carbon atoms locked into a rigid, ordered pattern. Some of these stellar crystals are estimated to be larger than Earth itself. They drift silently through the galaxy, cool and dark and ancient, the quietest jewels the universe has ever made. The coldest known white dwarfs have cooled over such immense spans of time that their surface temperatures approach something close to room temperature. They no longer glow visibly. They have faded below the threshold of what our eyes could detect, drifting through the galaxy as dark, silent remnants. Scientists locate them only through careful infrared observation. They are among the oldest objects we know of, patient survivors of an almost unimaginable stretch of cosmic time. Binary star systems are extraordinarily common. More than half of all stars in the galaxy share their journey through space with at least one companion. Two stars born from the same cloud of gas and dust, bound together by gravity, orbiting their shared center of mass in a slow, steady dance. Some pairs are so close they nearly touch. Others are separated by vast distances, taking thousands of years to complete a single orbit. The universe, it seems, prefers company. In a closed binary system, a white dwarf can slowly pull material away from its companion star. Gravity reaches across the small gap between them, drawing streams of gas from the companion's outer layers. That material does not fall directly onto the white dwarf. Instead, it spirals inward, forming a flattened disk of glowing gas called an accretion disk. The disk shimmers with heat as the infalling matter gradually works its way inward, layer by layer, settling slowly onto the white dwarf's surface. When enough material has accumulated on a white dwarf's surface, the layer of hydrogen can become so hot and dense that it ignites in a sudden thermonuclear explosion called a nova. The explosion is not destructive to the white dwarf itself, it is a surface event, a brief, brilliant flash. The accumulated hydrogen burns away in a matter of days or weeks, and then the process begins again, slowly and quietly, as more material drifts down from the companion star. A nova can briefly make a white dwarf millions of times more luminous than it normally appears. For a short time, a star that was invisible to the naked eye can become bright enough to see clearly in the night sky. Ancient astronomers noticed these sudden appearances and called them new stars, which is precisely what the word nova means in Latin. Then, over days and weeks, the light softens and fades, and the white dwarf quietly returns to its patient, dimly glowing self. If a white dwarf accretes enough mass to push beyond 1.4 solar masses, it does not simply collapse, it detonates entirely in a catastrophic explosion called the Type Ia supernova. The white dwarf tears itself apart in a runaway thermonuclear chain reaction, leaving nothing behind. No remnant, no core, just an expanding shell of brilliant light and scattered stellar material. These explosions shine so consistently that astronomers use them as cosmic measuring tools, reading the distances between galaxies by their glow. The Chandrasekhar limit, 1.4 solar masses, is the precise threshold beyond which a white dwarf can no longer hold itself together. Below that mass, the quantum pressure of electrons is enough to resist gravity's pull. Above it, that resistance fails, and gravity wins completely. This limit was calculated in the 1930s by the young physicist Subrahmanyan Chandrasekhar, who worked out the mathematics during a long ocean voyage. It remains one of the most elegant and important numbers in all of astrophysics. Let your body grow a little heavier now, sinking gently into wherever you are resting. There is nothing to hold on to, nothing to figure out. Let each breath come and go on its own, soft and unhurried. Your thoughts can drift like slow clouds, passing through without needing to stop. The universe is immeasurably vast and ancient, and right now, in this quiet moment, you are held safely within it. Simply rest. Simply breathe. Let everything soften and grow still. Stars far more massive than our Sun, those born with more than about 8 times the Sun's mass, meet a very different end. Rather than fading slowly into a white dwarf, they collapse and explode in what is called a core collapse supernova. The iron core at the heart of such a star, having fused all the lighter elements it can, suddenly gives way under its own weight. In less than a second, the core implodes, and the resulting shockwave tears the entire star apart from the inside out. In the span of just a few seconds, a core collapse supernova releases more energy than our Sun will radiate across its entire 10 billion-year lifetime. Almost all of that energy pours outward not as light, but as a flood of nearly massless particles called neutrinos, streaming away at nearly the speed of light. The visible explosion, brilliant as it is only a tiny fraction of what is actually released. It is one of the most energetic single events the universe is capable of producing, yet it passes quietly through almost everything it touches. After the fury of a supernova fades, something remains at the center. The collapsed core of the original star, crushed to extraordinary density, survives as a neutron star. It is not a star in the way we usually imagine. It no longer burns or fuses fuel. It is simply a sphere of matter compressed to its absolute limit, radiating the last of its heat into the surrounding darkness. Around it, the beautiful, tattered remnant of the explosion glows and slowly expands, a gentle cloud of light marking where a great star once lived. A neutron star is only about 20 kilometers across, roughly the size of a small city, yet it contains more mass than our entire Sun. If you could place one beside the Earth, it would appear as little more than a point. And yet, its gravity would be incomprehensible. All of that solar mass compressed into a sphere you could walk across in a few hours. The matter inside is packed so tightly that individual atoms no longer exist. Protons and electrons have merged into neutrons, pressed together with almost no space between them. Neutron star matter is so extraordinarily dense that a piece no larger than a sugar cube would weigh roughly 1 billion tons on Earth. That is the mass of a small mountain compressed into something you could hold between two fingers, if such a thing were ever possible to touch, which of course it is not. This density is near the very limit of what matter can be, while still remaining matter as we understand it. It sits at the edge of known physics, pressing against boundaries that our equations can barely describe. The gravity at the surface of a neutron star is roughly 200 billion times stronger than the gravity you feel right now. Standing on such a surface, were it in any way imaginable, you would be crushed instantly and completely. Even mountains on a neutron star can be no taller than a few centimeters, because anything taller would be flattened by the gravitational force. The surface is smooth almost beyond conception, a perfect sphere of compressed matter, held in the tightest possible grip of its own weight. When a massive star's core collapses, it falls inward with tremendous speed, and as it shrinks, it begins to spin faster and faster, just as a figure skater pulls in their arms and turns more rapidly. This is the conservation of angular momentum at work. A core that may have rotated slowly over many days suddenly collapses to a tiny fraction of its original size, and in doing so, its rotation accelerates enormously. The resulting neutron star can spin many times per second, a slow stellar giant transformed into something entirely new and astonishing. The fastest spinning neutron stars complete hundreds of rotations every single second. Where once a vast stellar core turned slowly over the course of days, the collapsed remnant now spins with breathtaking speed, dozens, sometimes hundreds of full rotations in the time it takes you to draw one quiet breath. The physics that governs this is elegant and inevitable. Angular momentum is conserved, and what was enormous and slow becomes tiny and impossibly swift. A rapidly rotating neutron star that emits beams of radio waves is called a pulsar. As the star spins, two narrow beams of radio energy sweep outward from its magnetic poles, like the beam of a lighthouse turning in the dark. If the Earth happens to lie in the path of one of those sweeping beams, we receive a pulse, a regular, repeating signal arriving from across the galaxy. Each pulse is a quiet hello from a spinning remnant star far away. Pulsars were first detected in 1967 by the astronomer Jocelyn Bell Burnell, who noticed a strangely regular signal repeating in her radio telescope data. The pulses were so perfectly timed that she and her colleagues initially called them LGM signals, LGM standing for Little Green Men, because nothing natural was known to produce such clockwork regularity. Of course, the source turned out to be natural. After all, a spinning neutron star, more precise than anything humanity had yet imagined. Let your body settle a little more deeply now into wherever you are resting. There is nothing you need to hold on to, nothing you need to figure out or remember. Each breath you take is slow and easy, arriving and leaving without any effort at all. Let your thoughts drift like clouds moving across a very wide, very quiet sky, passing through without catching, without pulling you anywhere. You are here, you are safe, and there is nothing left to do tonight but rest. The first pulsar ever discovered, known to astronomers as Sir B1919+21, pulses with extraordinary clockwork regularity once every 1.34 seconds. Every 1.34 seconds, without variation, a burst of radio energy arrives from that distant spinning star. It has been doing this for a very long time, ticking away across the darkness like the quietest possible clock. steady and unhurried, its rhythm older than anything we have ever built. Pulsar timing is so precise that it rivals the accuracy of atomic clocks here on Earth. The most stable pulsars keep time to within a few microseconds over many years, their rotation so steady that astronomers use them to detect tiny disturbances in the fabric of space-time itself. There is something quietly remarkable about that. A collapsed stellar remnant spinning in the dark, keeping better time than almost anything we have ever engineered. Nature arrived at this precision long before we thought to look for it. Millisecond pulsars are a special class of pulsar that spin hundreds of times per second, far faster than ordinary pulsars. They reach these extraordinary speeds because they have been gradually spun up over time, accreting matter from a nearby companion star. As material spirals inward and falls onto the neutron star, it transfers angular momentum, spinning the star faster and faster over millions of years. The result is a neutron star rotating with a smoothness and speed that almost defies imagination. The fastest spinning pulsar currently known to science is called SIR J1748-2446 AD, and it rotates 716 times every second. 716 full rotations in a single second, its equator moving at a significant fraction of the speed of light. It sits in a globular cluster called Tertzon 5, spinning away in the dark with a calm indifference to the strangeness of its own existence, ticking at a rate our senses could never follow. Not all pulsars announce themselves with radio waves. Some pulsars emit their sweeping beams in the form of X-rays, a far more energetic kind of light invisible to our eyes. These X-ray pulsars were discovered once telescopes were carried above Earth's atmosphere, where X-rays from space can finally be detected. The beams still pulse with that same steady rhythm, but they carry the signature of much more violent physical processes happening close to the neutron star's surface. X-ray pulsars are most often found in binary star systems, paired with a companion star from which they are steadily pulling material. Gas flows from the companion, spirals inward through an accretion disk, and finally falls onto the magnetic poles of the neutron star. The impact of that infalling material releases an enormous amount of energy as X-rays, creating the bright pulsing beams we detect. It is a quiet and ancient dance between two stars, one giving, one receiving, both changed by the exchange. A pulsar's magnetic field can be 1 trillion times stronger than Earth's magnetic field. Earth's own magnetic field is a gentle, invisible presence. It guides compass needles and shelters us from solar winds. But a pulsar's magnetic field is something of an entirely different order, almost impossible to hold in the mind. It warps the space around the star, shapes the very atoms on its surface, and channels energy into those sweeping beams with a force that dwarfs anything we encounter in our quiet corner of the cosmos. Magnetars are neutron stars with magnetic fields 1,000 times stronger than those of ordinary pulsars. They represent the most intensely magnetized objects that science has ever confirmed to exist anywhere in the universe. A magnetar carries within it a field so powerful that it fundamentally alters the behavior of atoms and light near its surface. Physicists believe that even the vacuum of space itself is changed in the immediate vicinity of a magnetar, stretched and polarized by the sheer intensity of its magnetic presence. The magnetic field of a magnetar is so intense it would erase a credit card from 1,000 kilometers away. That distance is roughly the span between two large cities, and yet from that remove, the field would be strong enough to strip away the magnetic information encoded on even the smallest everyday object. Scientists use this comparison simply to help the human mind reach toward a scale it was never built to grasp. The magnetar does not notice. It simply exists, humming with a force that rewrites the rules of the familiar world. Magnetars occasionally release colossal bursts of energy called starquakes, which send floods of gamma rays outward across space. Scientists believe these events occur when the immense magnetic field becomes so stressed and twisted that the solid crust of the neutron star suddenly shifts and fractures. The crust does not crack gently. It snaps in an instant, releasing energy stored over long, quiet years in a single tremendous pulse. And then, just as suddenly, the magnetar grows still again, and the darkness of space returns. There is nothing you need to hold on to right now. Let your thoughts drift the way light drifts across the surface of a calm, still sea, touching nothing, disturbing nothing. Feel the weight of your body settle a little more deeply wherever you are resting. Let your breathing find its own slow rhythm, unhurried and easy. You are here, and you are safe, and the night is very quiet. There is nothing left to do but let go, gently, and allow sleep to find you. A magnetar starquake in the year 2004 briefly outshone every other star in the sky in gamma rays, and it did so from 50,000 light-years away. The source was a magnetar called Skier 1806-20, sitting on the far side of our own galaxy. For a fraction of a second, it released more energy than the Sun produces in 250,000 years. Despite the almost incomprehensible distance, the burst was detectable from Earth, a whisper from across the galaxy, arriving in the night. There are only about 30 confirmed magnetars known to exist within the entire Milky Way. In a galaxy containing hundreds of billions of stars, 30 is a vanishingly small number, a handful of extraordinary objects scattered across an ocean of more ordinary stellar lives. Scientists believe there may be more, hidden behind clouds of dust and gas, their signals not yet reaching us. But for now, 30 known magnetars drift quietly through the galaxy, each one a singular and remarkable thing, rare beyond easy reckoning. Magnetar crusts can crack under the stress of their own magnetic fields, and when they do, the energy released in just 1/10 of a second exceeds everything the Sun will emit across 100,000 years. The numbers are too large for ordinary feeling, so simply let them rest in the mind, like distant music, enormous, quiet, and unhurried. The magnetar does not strain or struggle. It simply holds its impossible tension until the moment passes, and then it rests again, cooling slowly in the dark between the stars. Some neutron stars have surfaces covered in a crystalline lattice of iron nuclei, arranged with a geometric precision that mirrors the structure of a crystal here on Earth. The iron does not exist as the soft, workable metal we know. It has been compressed into a rigid atomic lattice, each nucleus locked in place by the enormous gravity pressing down from above. Scientists believe this crystalline crust is extraordinarily strong, perhaps the strongest solid material anywhere in the known universe, holding its perfect order beneath conditions of almost unimaginable pressure. Beneath the iron crust of a neutron star lies a region scientists call the inner crust, where free neutrons drift in a dense, quiet sea. The iron lattice above gives way to something stranger. Neutrons no longer bound inside atomic nuclei, but flowing freely through the interior in a state of matter that has no equivalent anywhere in our everyday experience. This sea of free neutrons is thought to behave like a superfluid, flowing without friction or resistance. Deep inside the neutron star, matter has become something entirely new, resting in the dark at the heart of a dead star. The deepest layers of a neutron star may contain exotic matter in states that physics has not yet found words to describe. Scientists believe that as pressure increases toward the very center, matter may transform into something entirely beyond our current understanding, phases of existence that have never been observed in any laboratory on Earth. The inner regions of a neutron star remain one of the great quiet mysteries of modern science, holding their secrets gently, far beyond our reach. Quark matter may exist inside the densest neutron stars, in a region where even the building blocks of protons and neutrons can no longer hold together. Ordinarily, quarks are confined inside particles, never free to roam on their own. But scientists believe that under the extraordinary pressures at the heart of the densest neutron stars, quarks may break loose and move freely through the interior, forming a new and alien state of matter, unlike anything else in the known universe. A hypothetical star made entirely of free quarks is called a quark star. It exists, for now, only in the realm of theory, a possibility that mathematics allows but observation has not yet confirmed. If such an object were real, it would be a world built from matter in its most unbound state, quarks flowing freely through its entire body, with no protons or neutrons to contain them. Scientists hold the idea gently, neither dismissing nor confirming it, letting it rest quietly among the open questions of the cosmos. Quark stars, if they exist, would be smaller and denser than even neutron stars. A neutron star is already almost incomprehensibly compact, but a quark star would compress that same mass into an even tighter space, its interior packed with freely flowing quarks rather than neutrons. Scientists calculate that such an object might measure only a handful of kilometers across, a tiny jewel of extreme matter resting in the dark, almost invisible against the vastness of space around it. The object known as RxJ 1856.5-3754 was once proposed as a candidate for a quark star. Astronomers noticed that it appeared smaller than a typical neutron star should be, its radius suggesting something more compact might lie within. The debate has settled somewhat over time, and most scientists now favor explanations within known physics, but for a while, this quiet object floating 40 light-years away held the possibility of being something entirely new. Let your body settle a little more deeply into the surface beneath you. There is nothing to hold on to right now, nothing to figure out or remember. The breath moves on its own, slow, easy, unhurried. Each exhale carries a little more of the day away. The mind does not need to follow every thought that drifts through. Simply let them pass like slow clouds and rest here in the quiet, warm, and still as the universe turns gently overhead. Strange quark matter, which contains a third type of quark called the strange quark alongside the more common up and down quarks, may be the most stable form of matter in the entire universe. This idea, known among scientists as the strange matter hypothesis, suggests that ordinary matter, the kind that makes up everything we can touch, may actually be in a higher energy state than strange quark matter. If true, strange quark matter would be the deepest resting place matter can find, the universe's most settled and enduring form. A strange star, made entirely of strange quark matter, would be wholly alien in its composition, built from a substance that has no counterpart anywhere in ordinary experience. Its interior would contain no protons, no neutrons, no familiar atomic nuclei, only strange quark matter from its surface, all the way to its center. Scientists believe such an object might have a thin crust of ordinary matter resting atop the strange core, a fragile, familiar layer over something utterly unlike anything else in the cosmos. Preon stars are a purely theoretical concept, imagined by scientists who ask what might happen if matter could be compressed even beyond the quark level. The idea begins with the possibility that quarks themselves might be made of even smaller constituents, sometimes called preons. If such particles exist, and if enough matter were compressed tightly enough, a preon star might form, an object so dense that it would make a neutron star feel spacious by comparison. No evidence for preons has yet been found, and preon stars remain a quiet speculation at the very edge of physics. If preon stars exist, they would be smaller than a city block, yet more massive than the Sun. The mind rests gently on that image, something you could walk around in a few minutes, yet containing more matter than our entire star. Scientists consider such objects purely hypothetical for now, with no observational evidence to confirm them. But the universe has surprised us before, and somewhere in the vast quiet dark, there may be objects waiting to be discovered that will reshape everything we think we know about the nature of matter. Electroweak stars are a theoretical type of stellar object, where the weak nuclear force itself steps in to balance the crushing inward pull of gravity. In an ordinary star, it is the outward pressure of nuclear fusion that holds gravity at bay. But in an electroweak star, scientists imagine a brief and extraordinary phase where the weak force, the same force responsible for certain kinds of radioactive decay, provides that counterbalance instead. These objects, if they exist at all, would be extraordinarily short-lived, lasting perhaps only a few seconds in cosmic terms. They are a quiet whisper at the very boundary between a dying stellar core and the formation of a black hole. Brown dwarfs are often called failed stars, objects that gathered enough mass to begin the journey toward starhood, but never quite arrived. To sustain the kind of hydrogen fusion that powers a true star, an object needs to reach a mass of at least about 80 times that of Jupiter. Brown dwarfs fall short of that threshold, forming in the same way as stars, but never igniting their hydrogen fuel in any lasting way. They are not failures in any sorrowful sense. They are simply something quieter, something gentler, drifting through the galaxy in their own unhurried way. Although brown dwarfs cannot sustain ordinary hydrogen fusion, many of them do experience a brief and gentle period of nuclear burning early in their lives. They are able to fuse deuterium, a heavier form of hydrogen, for a time, sometimes for tens of millions of years. This early warmth gives a young brown dwarf a soft inner glow, a temporary brightness before the fuel runs out and the long cooling begins. Over billions of years, a brown dwarf simply fades, growing dimmer and cooler, settling into a quiet dimness that it will carry for the rest of cosmic time. The coolest known brown dwarfs have surface temperatures lower than a kitchen oven set to its highest setting. Most stars burn at thousands of degrees, but some brown dwarfs have cooled to only a few hundred degrees Celsius at their surfaces. That is a remarkable thing to sit with, an object larger than any planet, containing more mass than any world we know, yet radiating heat at a level we might associate with something as familiar as baking bread. The universe contains wonders in every direction, and sometimes the strangest wonders are the quietest ones. Among the coolest of all brown dwarfs are those belonging to a class called white dwarfs, objects so cold that scientists believe water clouds may drift through their upper atmospheres. On Earth, water clouds are something we see every day, soft and white against a blue sky. But to imagine them forming around a stellar object, in the atmosphere of something born from the same collapsing gas clouds that make stars, is quietly extraordinary. White dwarfs represent the very coolest end of the stellar family, where the line between a star and a cold gas world begins to blur at the edges. One particular brown dwarf, known to astronomers as WISE 0855-0714, holds a remarkable distinction among all known stellar objects. Its surface temperature is estimated to be somewhere near the freezing point of water, close to 0 degrees Celsius. That means this object, born from the same cosmic processes that create stars, is barely warmer than an ice cube. It drifts through space only about 7 light-years from our own solar system, one of the Sun's nearest neighbors, yet so dim and cold it was only discovered in the year 2014. There is nothing you need to hold on to right now. Whatever thoughts are still drifting through your mind, you can simply let them pass, like slow clouds moving across a night sky. Your body is heavy and warm. Your breath is slow and even. Each exhale carries a little more of the day away. You are here, resting, and the universe is vast and quiet around you. There is nothing to figure out, nothing to remember. Only this soft darkness, this easy breath, this gentle drift towards sleep. Some brown dwarfs have cooled so thoroughly over their long lives that they begin to blur the ancient boundary between a star and a planet. They have temperatures, atmospheric chemistry, and cloud structures that resemble the giant planets of our own solar system, far more than they resemble any star. Jupiter, the largest planet in our neighborhood, and the coolest brown dwarfs exist in a strange shared territory where our categories soften and dissolve. The universe does not always arrange itself neatly into the boxes we build for it, and there is something restful in accepting that. Subdwarf stars occupy a quiet corner of the stellar family that is easy to overlook. They are smaller and hotter than ordinary main-sequence stars of the same color and spectral type, sitting just below the main band of stars on the diagram astronomers use to classify stellar life. A subdwarf of the same spectral class as the Sun, for example, would burn hotter and shine from a more compact body. They tend to be older stars, carrying the marks of a long life, their compositions shaped by the particular history of the galaxy at the time they were born. Hot subdwarf B stars are among the more unusual members of the subdwarf family, objects that have lost nearly all of their outer hydrogen envelopes, leaving behind a bare core running on helium fusion. Most stars hold on to their hydrogen layers throughout their lives. But these stars have been stripped, sometimes by a companion star pulling material away, sometimes through other processes scientists are still working to understand. What remains is a naked helium-burning core, exposed to space, burning in a way that most stellar cores never do. They glow with a hot blue-white light, quiet and steady, their unusual nature written in their very color. Extreme helium stars have surfaces almost entirely devoid of hydrogen, composed instead of layer upon layer of helium. Most stars wear hydrogen as their outermost skin, the most abundant element in the universe, but these rare objects have shed that familiar covering almost completely. What remains is an atmosphere of helium, with only the faintest traces of anything else. They burn quietly in the deep sky, their unusual surfaces a testament to how thoroughly a star's history can rewrite its own composition. Our coronae borealis stars are known for something deeply unusual. They dim unpredictably and dramatically, sometimes fading by several magnitudes within weeks, as vast clouds of carbon soot condense around them. One moment they shine steadily, the next, a dark veil of carbon particles gathers and dims their light, as though a curtain is being drawn. The dimming can last for months before the soot disperses, and the star slowly brightens again. There is a quiet rhythm to this, a slow breathing in and out of light. Carbon stars carry so much carbon in their outer atmospheres that carbon-bearing molecules come to dominate their entire spectra, giving them a distinctive deep reddish hue, unlike almost any other star. In most stars, oxygen binds with carbon and leaves little carbon free, but in these objects the carbon is so abundant that it saturates the available oxygen and still has plenty left over. The result is a star that glows with a rich, deep red warmth, its light filtered through a veil of carbon molecules drifting in its upper layers. S-type stars occupy a gentle middle ground in stellar chemistry, sitting precisely at the boundary between stars whose atmospheres are dominated by oxygen and those dominated by carbon. In an oxygen-rich star, carbon is locked away into carbon monoxide molecules, leaving oxygen free. In a carbon star, the reverse is true. S-type stars have achieved a rare near balance between the two, with zirconium oxide molecules appearing prominently in their spectra as a quiet signature of this chemical equilibrium. They are stars caught softly between two worlds. Lithium-rich giant stars present a quiet puzzle to astronomers, because by all accounts, lithium should not survive inside a star. The interior temperatures of a giant star are more than hot enough to destroy lithium nuclei, consuming them in nuclear reactions long before they could ever appear at the surface. And yet some giant stars display surprisingly high levels of lithium in their outer layers. Scientists believe these stars may be creating or dredging up lithium through processes not yet fully understood, a small mystery resting gently in the data. Barium stars carry an unusual chemical signature on their surfaces, an enrichment of barium and other heavy elements that should not be there in such quantities. The explanation is a story of stellar companionship written across time. These stars once had a partner, a more massive companion that evolved into an asymptotic giant branch star and, during that phase, produced heavy elements through slow neutron capture deep in its interior. Material from that companion drifted across to the barium star's surface, leaving a chemical record of a relationship that has long since ended. Thorn-Geit-Kao objects are one of the most extraordinary theoretical constructs in stellar physics. Stars that contain, hidden within their enormous outer envelopes, a neutron star at their very core. The idea was proposed by Kip Thorne and Anna Geit-Kao in 1977. In their model, a neutron star spirals into the center of a red giant or red supergiant, becoming embedded there, the two objects merging into a single strange hybrid. The neutron star does not destroy the giant. Instead, it quietly takes up residence inside it, powering the star from within. Let your body settle a little more deeply now. There is no need to hold any thought in particular. Whatever is still moving through your mind, you can allow it to slow, to soften, to drift away like the last light fading from a distant star. Your breath is steady. Your shoulders are easy. The quiet is all around you, and you are held within it. There is nothing to solve and nothing to carry. Only rest, only stillness, only the soft dark of a night that is entirely yours. From the outside, a Thorn-Geit-Kao object would appear entirely unremarkable to a distant observer. It would look, to all outward appearances, like an ordinary red supergiant star. The enormous outer envelope of cool, glowing gas would hide completely what lies within. No visible sign of the neutron star at its center would betray its presence. The star would simply glow with that familiar deep red warmth, enormous and slow, giving nothing away. The strangeness would be entirely interior, invisible, a secret kept by the star itself. 112, a star located in the Small Magellanic Cloud, roughly 200,000 light-years away, is considered one of the most promising candidate Thorn-Geit-Kao objects yet identified. Astronomers studying its spectrum found unusual abundances of certain heavy elements, rubidium, lithium, and molybdenum, that match theoretical predictions for what a neutron star-powered interior might produce. Scientists are careful to note that the evidence is suggestive rather than conclusive, and further study is ongoing. But for now, it rests quietly in a neighboring galaxy as a gentle hint that these strange hybrid stars may truly exist. Symbiotic stars are binary systems where a red giant and a white dwarf orbit one another in a close, quiet partnership. The red giant, vast and cool, slowly sheds material from its outer layers. The white dwarf, dense and patient, draws that material toward itself across the space between them. The two exist in a kind of slow celestial conversation, exchanging matter across the dark, their differences making them inseparable companions across millions of years. Cataclysmic variable stars flare unpredictably as a white dwarf accretes matter in sudden, irregular bursts. Material builds on the white dwarf's surface over time, quietly accumulating until conditions ignite a brief thermonuclear flash that brightens the system dramatically. Then the light fades, and the slow gathering begins again. There is a gentle rhythm hidden within the unpredictability, a cycle of quiet accumulation and soft release, repeated across immense spans of time. AMCVN systems are ultra-compact binaries, where both members are white dwarfs, orbiting one another in an extraordinarily tight embrace. Their orbital periods are among the shortest of any known stellar systems. Some complete a full orbit in as little as 5 to 10 minutes. The two white dwarfs circle so closely that they are separated by a distance smaller than the diameter of the Earth. They are locked together in a slow, intimate spiral that will last for millions of years. M7 binaries will eventually merge as the two white dwarfs slowly spiral inward over millions of years, drawn together by the gentle but relentless loss of energy to gravitational waves. When they finally meet, the result may be something entirely new, a stellar remnant unlike any other, perhaps a rapidly spinning single white dwarf, or something stranger still. Scientists are still working to understand exactly what emerges from that quiet final union. Whatever it becomes, it will be a new kind of object in the universe. Luminous blue variables are among the most massive and brilliant stars known to exist, hypergiants burning with extraordinary ferocity. Unlike most stars, they are not stable. They periodically undergo enormous eruptions, suddenly brightening and shedding vast quantities of their outer material into space. These outbursts can last years or even decades. They are not supernovae, the star survives. But each eruption strips away more of the star's outer layers, slowly revealing what lies deeper within. Eta Carinae is one of the most remarkable stars in the known galaxy, a luminous blue variable that underwent a colossal eruption in the 1840s, now called the Great Eruption. During that event, it ejected somewhere between 10 and 40 solar masses of material, an almost incomprehensible amount, out into the surrounding space. For a brief time, it became the second brightest star visible in the night sky. Then it faded, leaving behind a transformed landscape of gas and dust that continues to expand to this day. Eta Carinae is surrounded by a beautiful bipolar nebula called the homunculus, formed from the material ejected during the Great Eruption of the 1840s. The homunculus takes the shape of two lobes, one above and one below the star, like a pair of enormous glowing bubbles expanding outward in opposite directions. It stretches across roughly 1 light-year of space. The nebula glows with warm reflected light from the star within, a soft and lasting monument to one of the most violent stellar events in recorded history. Wolf-Rayet stars are extraordinary objects that blow off their outer layers in ferocious stellar winds, among the most powerful winds produced by any kind of star. These winds stream outward at speeds of thousands of kilometers per second, carrying enormous quantities of mass away from the star and into the surrounding space. Over time, the star loses a significant fraction of its total mass this way. The winds carve great glowing cavities and shells in the surrounding gas, reshaping the neighborhood of space around them. Let yourself rest now, just as you are. There is nothing more to follow, nothing more to hold. Your body is heavy and warm, sinking softly into wherever you lie. Your breath moves in and out without any effort at all. The thoughts that remain are growing lighter, thinning like mist in a gentle breeze. You are drifting slowly and peacefully toward the quiet dark of sleep. Let the stars keep their watch above you. You have nothing left to do but let go. Wolf-Rayet stars expose their bare nuclear-burning cores to the universe, stripped of the outer hydrogen envelopes that most stars wear throughout their lives. What remains is the innermost layer of the star, the hot, dense, furiously burning core itself, laid bare to open space. These cores burn at surface temperatures of 50,000 Kelvin or more, blazing with blue-white intensity. They are among the hottest stellar surfaces known, naked fires at the edge of what a star can be. Some Wolf-Rayet stars produce carbon-rich dust clouds in their stellar winds, and these clouds drift outward and thicken periodically, gently dimming the star as seen from afar. The carbon forms in the cooling outer edges of the wind, condensing into tiny grains the way frost forms on a cold surface. As these clouds grow and spread, they absorb some of the star's brilliant light, causing it to fade softly and then brighten again as the clouds disperse. It is a slow, rhythmic breathing of dust and light. 104 is a Wolf-Rayet star whose carbon-rich dust forms a perfect pinwheel spiral, a delicate rotating pattern visible from Earth through careful observation. As the star and a close companion orbit each other, the dust released in the wind wraps into this elegant spiral shape, winding outward turn by turn like a slow cosmic whirlpool. The spiral extends over a vast region of space, yet from our vantage point it appears as a beautifully symmetrical pattern, one of the most graceful structures any star has ever made. Population trait. Stars were the very first stars in the universe, forming in the quiet dark of the early cosmos from nothing but pure hydrogen and helium, the only elements that existed at that time. There were no heavier elements yet, no carbon, no oxygen, no iron, only the two lightest gases drifting together under gravity in the vast cool darkness. These first stars were born into a universe that had never seen starlight before. When they ignited, they were the first light in a cosmos that had been dark since its beginning. Population Dree. Stars may have been hundreds of times more massive than the Sun, enormous beyond anything that forms in the universe today. Scientists believe the absence of heavier elements meant the gas clouds of the early universe could not cool efficiently, so instead of fragmenting into many smaller stars, they collapsed into single objects of staggering size. These were giants of a kind that no longer exists, burning with extraordinary intensity, flooding the young universe with ultraviolet light and reshaping the gas around them. No population tree star has ever been directly observed, because they all lived and died long before the universe looked anything like it does today. Their lives were brief by cosmic standards. The most massive stars burned the fastest, and they exhausted their fuel and collapsed billions of years before our sun was born. We have never seen one with our telescopes, and we may never see one directly, yet we know they existed, because the heavier elements they forged and scattered are woven into every star, planet, and living thing that came after them. Zombie stars are white dwarfs that survive a partial supernova explosion and continue to exist, which should not be possible. In a typical type Ia supernova, a white dwarf crosses a critical mass threshold and detonates completely, leaving nothing behind. But in some rare cases, something goes differently. The explosion is incomplete, the white dwarf partially survives, and it continues on, scarred and changed, but still present. Scientists believe these objects are real, wandering the galaxy as strange remnants of an event that was supposed to end them. Lib 4365 is a runaway white dwarf thought to be a zombie star, the surviving remnant of an incomplete supernova explosion. It is moving through the galaxy at extraordinary speed, flung outward by the force of the partial detonation that failed to destroy it. Its surface shows unusual chemical signatures. Enriched with elements forged in the heart of the explosion, it somehow survived. It travels alone now, carrying within itself the evidence of a cataclysm it passed through and outlasted, drifting quietly through the long dark between the stars. Hypervelocity stars have been flung out of the Milky Way at millions of kilometers per hour, moving so fast they will eventually leave the galaxy entirely and travel alone through intergalactic space. Most stars spend their entire lives bound to the galaxy by gravity, following slow orbits that take hundreds of millions of years to complete. But hypervelocity stars have been accelerated to speeds that gravity can no longer hold, sent on a one-way journey outward. They carry the light of our galaxy with them into the vast and empty dark beyond. US 708 is a hypervelocity star traveling fast enough to escape the Milky Way entirely, one of the fastest stars ever measured. Scientists believe it was once part of a binary system involving a white dwarf And when that white dwarf exploded, the companion was released like a stone from a sling, launched outward at tremendous speed. It is already well beyond the main body of the galaxy, moving farther away with every passing moment. It will drift through intergalactic space for billions of years, a single quiet light in the immense dark between galaxies. Let yourself be still, now, completely still. There is nowhere to go, nothing to reach for, nothing left to understand tonight. Feel the weight of your body resting, held gently and completely. Your breath is slow and easy, moving on its own without any help from you. The thoughts that still drift through your mind are growing softer, thinner, more like shadows than sounds. You are sinking, slowly and peacefully, into rest. The stars above are quiet. The universe is vast and calm. You are safe, and you are drifting, and sleep is very close now. Hypervelocity stars are thought to be ejected by close encounters with the supermassive black hole at the center of the galaxy, flung outward by gravitational forces of extraordinary magnitude. When a binary star system wanders too close to that immense central darkness, one star can be captured while the other is hurled away at incredible speed. The process is quiet in cosmic terms, a brief gravitational exchange that sends a star on a journey lasting billions of years. It is a gentle reminder that even the most dramatic departures in the universe unfold slowly, on timescales too vast to feel like urgency. Boson stars are a purely theoretical construct, imagined to be made entirely of exotic boson particles rather than ordinary matter. They would have no solid surface, no nuclear burning, no light of their own in the familiar sense, held together instead by quantum pressure from particles that do not behave like anything we can touch or see. Scientists have explored their mathematics with great care, finding that they could, in principle, exist without violating any known physical law. They remain a quiet possibility, a shape that the universe might allow, waiting patiently in the realm of the theoretical. Dark matter stars, sometimes called dark stars, may have powered the very early universe through a process called dark matter annihilation, long before ordinary nuclear fusion lit the first familiar suns. In the earliest moments after the Big Bang, dark matter was far more concentrated than it is today, and clumps of ordinary hydrogen and helium may have been heated from within by colliding dark matter particles. These dark stars would have glowed without burning in the conventional sense, warmed by invisible collisions deep in their interiors. They are a gentle mystery from the universe's first chapter, imagined but never yet seen. A dark star would be enormous and remarkably cool compared to the blazing stars we know today, powered by an entirely non-nuclear energy source hidden deep within its vast body. Scientists believe these objects could have swelled to sizes hundreds of times larger than our Sun while remaining relatively dim, their surfaces warm rather than searingly hot. There would be no fusion fire at their hearts, only the slow, quiet release of energy from matter and antimatter meeting in the dark. They would have drifted through the young universe like enormous warm lanterns, gentle and immense, before eventually fading as their dark matter fuel was exhausted. Planck stars are a deeply speculative concept arising from a branch of physics called loop quantum gravity, where the collapse of matter does not end in a true singularity, but instead rebounds. According to this idea, matter compressed to the smallest meaningful scale of space and time would encounter a quantum pressure strong enough to reverse the collapse, bouncing outward in an event that might eventually be detected as a faint burst of radiation. The timescales involved are almost incomprehensibly long, far beyond the current age of the universe. It is a quiet and beautiful thought that even the most extreme collapse in nature might carry within it the seed of a gentle return. Black holes are the final fate of the most massive stellar cores, the endpoint reached when a star far heavier than our Sun exhausts its fuel and its core collapses beyond any force that can stop it. After the supernova has faded and the outer layers have been scattered into space, what remains falls inward without limit, compressing into a region of space where gravity overwhelms everything we know. A black hole does not burn or shine in any ordinary sense. It simply exists, a place where space-time curves so deeply that nothing, not even light, can find its way back out. The event horizon of a stellar mass black hole is only a few kilometers across, a boundary so small it would be invisible against the vastness of space, were it not for the way it bends and darkens everything around it. This invisible threshold marks the point of no return, the place where the escape velocity reaches the speed of light. A traveler approaching it from outside would see the surrounding stars shift and distort, the universe warping gently around the edges of that small dark circle. It is one of the most extreme boundaries in nature, and yet in the scale of the cosmos it is no larger than a small city. Time dilation near a black hole's event horizon means that an outside observer would never quite see matter cross it, watching instead as in falling objects slow and dim and seem to freeze at the boundary, fading gradually into the dark. This is not an illusion but a real consequence of the way gravity stretches time itself, causing clocks near the horizon to tick more and more slowly relative to those far away. From the perspective of the falling object, the crossing happens smoothly and swiftly, but from far away, the universe watches it approach forever, softly, without a rival. It is one of the quietest paradoxes in all of physics. Hawking radiation is a theoretical process by which black holes very slowly lose energy and mass over immense timescales, proposed by the physicist Stephen Hawking in 1974. Near the event horizon, quantum effects allow pairs of particles to briefly emerge from the vacuum, and occasionally one escapes while the other falls inward, carrying a tiny amount of the black hole's energy away into space. The process is extraordinarily slow, and the radiation extraordinarily faint, far too dim to detect with any instrument we currently possess. But in principle, given enough time, even a black hole will quietly and gently fade. A stellar mass black hole would take far longer than the current age of the universe to evaporate completely through Hawking radiation, the process unfolding across timescales so vast they have no comparison in ordinary experience. The universe today is about 13.8 billion years old, and a black hole born from a collapsed star would require something closer to 10 to the power of 67 years to fade entirely, a number so large it barely fits inside the imagination. By then, all the stars will be long gone, the galaxies dark, the cosmos cold and still, and yet quietly, patiently, the last black holes will continue their slow and imperceptible dissolving into the gentle dark. Let your body soften now, just a little more. Feel the weight of your limbs settle gently, the way a leaf comes to rest on still water. There is nothing left to hold on to tonight, nothing to solve, nothing to remember. Let each breath arrive slowly and leave even more slowly, carrying with it whatever remains of the day. You are safe, you are still, and the universe is quietly turning all around you. Gravastar theory proposes that what we call black holes may actually be shells of exotic dark energy, hollow structures where the interior is not a singularity, but a region of repulsive energy held in delicate balance. The idea was proposed in the early 2000s as a way to resolve some of the deep puzzles surrounding what happens at the center of a collapsed star. From the outside, a gravastar would look almost identical to a black hole, bending light and space in the same familiar way. But inside, rather than infinite density, there would be only a quiet, pressurized stillness. It remains a theoretical possibility, a gentle alternative hiding beneath the surface of one of physics' most enduring mysteries. Fuzzball theory, emerging from the mathematics of string physics, suggests that what we call a black hole is not a void with a singularity at its heart, but rather an extraordinarily dense tangle of tiny vibrating strings, filling the entire region. In this picture, there is no true event horizon, no point of no return, only a vast and intricate web of string-like structures compressed into an almost unimaginably small space. The surface of a fuzzball would be a complex, fuzzy boundary rather than a sharp geometric edge. Scientists believe this framework might resolve the long-standing puzzle of what happens to information that falls into a black hole, allowing it to be encoded in the tangle rather than lost forever. It is a picture of the cosmos woven from the finest possible threads. The coldest possible stellar remnant is something called a black dwarf, a white dwarf that has radiated away all of its stored heat over an almost incomprehensible span of time, cooling until its temperature approaches absolute zero. Absolute zero is the coldest temperature that physics allows, the point at which all thermal motion ceases and matter becomes as still as it can ever be. A black dwarf would be a dark, dense, crystalline sphere drifting silently through space, no longer glowing, no longer warm, a perfect monument of stillness. It would be invisible against the dark, detectable only by the gravity it carries quietly within it. In many ways, it is the most peaceful object imaginable, a star that has finally, completely come to rest. No black dwarfs exist anywhere in the universe yet, because the cosmos is simply not old enough for even a single white dwarf to have fully cooled to that final stillness. The universe is about 13.8 billion years old, and the fastest cooling white dwarfs would still require trillions upon trillions of years to reach the temperature of a black dwarf. The oldest white dwarfs we know of have cooled to only a few thousand degrees, still faintly warm by stellar standards. Black dwarfs belong entirely to the far future, to an era so distant it lies beyond the reach of any clock we can imagine. They are stars that will exist one day, waiting patiently in the deep future like a promise the universe has not yet kept. The last stars in the universe will be red dwarfs, those small, slow-burning embers that consume their fuel so frugally they can shine for up to 100 trillion years, long after every sun-like star has swelled and faded, long after every massive star has exploded and gone dark. The red dwarfs will still be quietly glowing, dim and steady and patient in the cooling dark. They will be the final campfires of the stellar age, scattered across a universe that has otherwise grown cold and still. 100 trillion years is a span so vast that the current age of the universe fits inside it roughly 7,000 times over. And yet even they will eventually exhaust their fuel and fade, leaving the cosmos in silence. After all the stars have died, the universe will enter what scientists sometimes call the Dark Era, a vast and silent epoch populated only by remnants, white dwarfs cooling toward blackness, neutron stars spinning ever more slowly, black holes drifting alone through the dark. There will be no new light, no fusion, no warmth generated anywhere in the cosmos. The galaxies will have dispersed, their stars long gone, their black holes slowly evaporating through Hawking radiation across timescales that dwarf even the stellar age. It is not a frightening image, but a profoundly restful one, the universe itself finally growing quiet, settling into a stillness as deep and as complete as the deepest sleep. The strangest stars in the universe remind us, gently and without alarm, that matter under extreme conditions behaves in ways that challenge every known law of physics, that the cosmos is richer and more surprising than any single mind can hold. From the steady warmth of a red dwarf to the crystalline silence of a cooling white dwarf, from the impossible density of a neutron star to the theoretical whisper of a gravistar. Each of these objects is a quiet testament to how much wonder is woven into the fabric of everything. And you, resting here beneath the same sky that holds all of this, are made of the same atoms that once burned inside stars. You are part of this story, not separate from it. Let that thought settle softly as your breathing slows. The universe is vast and ancient and extraordinarily strange, and tonight it is holding you gently while you sleep. Good night.